So in the last class we discussed this first law of diffusion, Fick's first law of diffusion. According to this Fick's law, the diffusion flux is proportional to the concentration gradient. From that we derive the equation for diffusion, that is the diffusion flux is equal to minus d into diffusivity into concentration gradient. So this is the Fick's first law. So next we are going to discuss this Fick's second law. Okay, Fick's second law, and this time this time non-steady state diffusion. So I will explain later that. So the Fick's first law explained Fick's first law explain gives the relationship between the mass flow rate and the relationship between the first law gives the relationship between the mass flux and the concentration gradient. So J equal to, we can say J, the mass flux is equal to minus D into dou C by dou X. So that is the concentration gradient. Okay, so Fick's first law explain this relationship. So next we are going to discuss the Fick's second law. Fick's second law. So for that, I am considering a material with a different concentration of its constituents. Okay, so here the concentration is very high. In this left hand side, the concentration is very high, and towards the right, the concentration is very low. Towards the right, the concentration is very low, but the left hand side, the concentration is very high. Okay, so I consider this type of material. In one side, the concentration is very high, and the second side, the concentration is very low. So here we can see. Okay, and in this, I am going to draw the concentration versus distance profile. Okay, so this is the area we are covering, that is the distance x, and this y direction gives the concentration along the x direction. Okay, the y-axis show the concentration along the x direction. So here we can see the concentration variation like this way. This is the concentration variation. Okay, and here I am drawing a curved line. I will explain what is the reason for that. So this is the concentration variation, and here I am taking two sections or 2 points in the material, and in this point here I am taking this point, and in this point we got a particular amount of concentration. Okay, this is the concentration corresponding to this position of the material. I am taking another position, this position, and corresponding concentration we can find out from this graph. This is the concentration. Okay, and here I can draw a find out the slope of this graph. This is the slope of this graph at this point, and here this is the slope at this point. Okay, slope at this point. Okay, so here while diffusion, here we can see this is the area of high concentration, this is the area of low concentration, so there will be a diffusion from in this direction. Okay, this is the direction of diffusion. Okay, so there will be mass flow, and when the mass flow across this cross section or across this cross section, we can say the mass flux is equal to Jx. Jx is the mass flux. So Jx is the mass flux here. Okay, we can see here, this is Jx. And so this is the amount of atoms or particle crossing this section per unit area per time per second. So that is the unit of this flux. What is the unit? The atoms or particles crossing unit cross-section per unit time or kilogram per meter square per second. We can use any of the units. Okay, so here in this case, the uh, total atoms or kilogram mass of particles crossing this unit cross-section per time is equal to Jx. Similarly, here amount of particle crossing unit cross-section per time is equal to, I am giving another flux that is equal to J x plus delta x. Here it is x plus delta x. So in this cross-section it is Jx, here Jx plus delta x. Okay, and here in this position, this position is equal to x, and this position is equal to x plus delta x, this position. Okay, and the distance between these two regions will be, here it is x, here it is x plus delta x. So this distance will be delta x. This distance will be delta x. Okay, so here I am going to apply the fixed first law at junction x and x plus delta x. I am going to apply the fixed first law. What is fixed first law? J is equal to minus d into dou c by dou x. Okay, and here we can see the concentration is, our concentration gradient is different. Dou c by dou x is different here at x and x plus delta x, concentration gradient is different. Okay, and next we are going to find what is the change happen in the concentration for a volume. Here this is delta x and we have cross-section area. Cross-section area is equal to A. Okay, then what is the volume? Volume will be equal to A into delta x. A into delta x. That is the volume. So here I am going to find out what change happen in the concentration in the volume delta V. So here I am giving delta V. What is the change in the concentration in this volume, delta V volume, as a function of time? Okay, when the time change from T1 to T2 or delta T time, what is the change in the concentration on this volume? That is I am going to calculate. Okay, so what is the concentration change in delta V? The concentration change in delta V volume that I am going to calculate. How can we calculate this change in the concentration for this delta V volume? That is equal to mass entering this junction X. Okay, mass entering this volume along the junction X at a time interval delta T minus mass leaving this junction from this volume at the time interval delta T. That is the concentration change. Concentration change in delta V is equal to some amount of particle will enter at a delta T time. Okay, so the mass of particles entering this volume at a delta T time minus some of the particle will leave this junction from delta V volume for a time delta T second. So total mass of particle leaving this volume for delta V delta T second. That difference is the concentration change in delta V volume. Okay, so next I am going to calculate the mass entering delta V at X at this junction. At this junction, how much amount of mass is entering? Okay, so that is equal to at in time interval delta T. delta t, mx equal to jx into a into delta t. That is the mass of particles entering this junction, entering this junction into delta V volume for a time delta t. How, from where this equation, we got this equation? From this definition of J. From the definition of J, we got this equation. What is the definition of J? So J is
Mass.
equal to kilogram per meter square second. Okay, then mass equal to J into meter square means area. S means delta T. So if you want to calculate mass, then this flux into diffusion flux into area into second. That is equal to mass. So that is the equation. The diffusion flux into area into time interval. So that is the mass of mass entering the delta V for a time interval of delta T. Then mass of particles leaving delta V at x plus delta x in delta T time equal to that is, we can give mx plus delta x equal to how much amount of mass crossing this junction for a time of delta t. How can we find? We can use the same equation. Instead of jx, we can give here in this x, it is jx, but here in this x plus delta x, it is jx plus delta x. So here we can see x plus delta x, jx plus delta x, okay, into a into delta t. A into delta t. That is the amount of mass leaving delta V at a time interval of delta t from this x plus delta x junction, this junction. So if you take the difference between these two mass, that is the amount of concentration accumulated, mass accumulated in that volume. The mass accumulated in this volume equal to amount of mass leaving minus mass entering. Sorry, mass entering minus mass leaving. That is the amount of particles accumulated in this delta V. So next I am going to calculate that. So mass, നിങ്ങൾക്ക് കാണാൻ പറ്റുന്നുണ്ടോ പ്രോപ്പർ ആയിട്ട്?
Yes, sir.
Mass accumulating in delta V equal to mass accumulating in delta V is equal to delta M. We can give mass accumulating in delta V is equal to delta M. That is equal to mx minus mx plus delta x. Okay, so that is the amount of mx is the mass entering this volume. Mx plus delta x is the mass leaving the volume. So mass accumulating in this volume is equal to mx minus mx plus delta x. Okay, so we can give substitute this value. So mx is equal to jx into a into delta t minus mx plus delta x is equal to jx plus delta x into a into delta t. That is equal to a into delta t into jx minus jx plus, sorry, small letter jx plus delta x, a into delta t. That is the amount of mass accumulating. And here again we can rewrite this. That is equal to a into delta t into jx minus jx plus delta x. That is actually change in flux across that volume. Okay, change in flux across this volume. That is jx minus jx plus delta x. Okay, so we can give that value as delta j. Actually, delta j is equal to jx plus delta x minus jx on. Okay, so here we can give minus delta j. minus delta j. Actually, jx plus delta, this is the higher quantity. So x plus delta x minus jx is equal to delta j. So here jx minus jx plus delta x, so we gives a minus. So we got delta m equal to a delta t into minus of delta j. Okay. Then what is the concentration change? Concentration change is equal to concentration change is equal to delta C equal to delta M by delta V. That is the concentration change. Okay, so we already calculate delta M. So we can substitute this value minus delta J into delta T into A by what is delta V here? Cross section area is equal to A. This distance is equal to delta X. So A into delta X is equal to delta V. Okay, so we can give A into delta X. A into delta X. So these A times cancel each other. We got finally minus of delta J, sorry, minus of delta J divided by delta X into delta T. That is the change in concentration. Change in concentration is equal to minus of delta J by delta X into delta T. Okay. So that is the change in concentration. So from this, we can write delta C by delta T equal to, from this we can write delta C by delta T equal to this delta C equal to delta J by delta X into delta T minus of. So delta T is come to denominator, then delta J by delta X. Delta C by delta T equal to delta J by delta X. So this is the concentration change with respect to time. So this is delta C by delta T. This equation delta C by delta T equal to delta J by delta X. Okay, we got this equation. And here, what is this? The average change in concentration with for a time interval of delta T equal to rate of change of flux with respect to x coordinate. So during diffusion process across this particular volume, here across this volume, change in concentration, average change in concentration for a time delta T equal to average change in flux for for x coordinate with respect to x coordinate. So that is this equation. Okay. So and next I'm going to apply the limit for this equation. So I'm going to apply the limit. So here in this equation, limit delta t tends to 0, limit delta t tends to 0, delta c by delta t equal to, here we have a minus sign. So I forgot to give the minus sign. We have a minus sign here. Minus of limit delta x tends to 0, limit delta x tends to 0, delta j by delta x. Okay, delta j by delta x. limit delta t tends to 0, delta c by delta t equal to minus limit delta x tends to 0, delta j by delta x. Okay. So what is this? What is the meaning of delta t tends to 0? That means that time interval is tends to 0. That means that is the instantaneous concentration change. This delta t becomes instantaneous concentration change when delta t tends to 0. So the instantaneous concentration change across this volume is equal to instantaneous flux change. Okay, that is the rate of change of in a particular position in space than average value. Here delta j by delta x is actually average value of change in flux. But when we supply limited delta x tends to 0, that is the change in flux at a particular position. If you take a position, what is the change in flux? That gives delta j, limit x tends to 0, delta j by delta x. So that is the by applying the limit values. So from this, finally we got dou c by dou t equal to minus of dou j by dou x. So this is the second law of fix. Dou c by dou t is equal to minus of dou. We remove the limiting times with the converted into partial form. So dou c by dou t is equal to minus dou j by dou x. That is the second law of fix. Second law of fix. Dou c by dou t is equal to minus dou j by dou x. So this is the equation. Okay, this equation is not given in this. Dou c by dou t is equal to, this is a first form. This is our second law of fix and first form of second law. This is a first form. Okay, this is the first form. And we can derive the second form by just a second. Just a second. Okay, so this is the first form of fixed law, and then second form can be developed by applying first fixed law on this second fixed law. Okay, so next I am going to develop the second form of second law of fix. For that, I am going to apply the first law. What is the first law of fix? J equal to minus d into dou c by dou x. Okay, so here I am replacing this j value with the first law. Okay, I can replace this j value with this first law. So what happened? Dou c by dou t equal to minus of dou by dou x into, instead of j, I am giving this value minus d into dou c by dou x. Okay, from this we got dou c by dou t equal to dou square d into dou square c by dou a square. So this is the second form of fixed law. Dou c by dou t is equal to d into dou square c by dou x square. That is this equation. Dou c by dou t is equal to d into dou square c by dou x square. This is the second law of fix. Now what are the terms here? Dou C by dou T. That is an instantaneous change in concentration. Instantaneous change in concentration. That is dou C by dou T. Equal to D is the diffusivity and dou square C by dou F square. Okay. Here D is a constant value and this is the differential equation and this is the diffusion equation in a mathematical form. Okay. So and here the here C value is a concentration, but C can be any variable. It can be any variable. It no need of concentration. It can be any parameter or variable. Okay, and that is the variation of that variable with respect to time. Okay, here it is concentration. It can be any variable. So dou C by dou T, that is the instantaneous change. And here related to what is this second differential coefficient with respect to space, that is the dou square C by dou S square. Second differential coefficient with respect to space. Okay, and here the coefficient is C concentration and diffusivity. So this is the second law of Fick's. So first law, this one, J is equal to minus D into dou C by dou X. Second law is dou C by dou T is equal to D into dou square C by dou X square. Okay, so that is the first law and the second law of Fick's. Any doubt? Any doubt?
Yes, sir.
Okay. So ഇപ്പൊ ഈ ഇത് ഞാൻ സ്ലൈഡിൽ ഇൻക്ലൂഡ് ചെയ്തിട്ടില്ല. സോ നിങ്ങളത് സ്ലൈഡിൽ ലെക്ചർ കേൾക്കുമ്പോൾ അത് എഴുതി വെച്ചോളൂ കേട്ടോ. ഫസ്റ്റ് ലോയും സെക്കൻഡ് ലോയുടെ ഡെറിവേഷൻസ്. Okay.
Okay.
Then steady and unsteady state of diffusion. So steady state diffusion means that the concentration is independent of time. Here when we plot the concentration with respect to x, that is the distance. For example, in the previous case, here this is the distance x. So this is the concentration with respect to x. So here, when the concentration is independent of time, okay, so concentration is independent of time, then we can say that is, we can see when we plot this graph, if everywhere the slope is same for this line, then we can say that is a steady state. Okay, so with respect to time, there is no change in the concentration. Concentration is across the line, it is gradually decreasing, and there is no change in the concentration with respect to time. But in case of unsteady state diffusion, we can see the concentration is varying here at a particular time, t1 time. This is a graph. This is the graph at a t1 time. Okay, when we check the concentration difference in another time or variation of concentration in another time, this is the another graph, next graph. And for another time t3, this is the next graph. So with respect to time, the concentration is varying along the length of the diffusion or in the direction of diffusion. The concentration is vary with respect to time. Then that type of diffusion is called unsteady state diffusion. Unsteady state diffusion. Okay. So here in case of Fick's law, so Fick's law, the Fick's first law is applicable only to steady state. So that is actually a misconception. That's wrong. So that is why I said initially this is wrong. Steady state diffusion Fick's law. Okay, Fick's first law can be applied for both steady state and unsteady state of diffusion. Okay, and second law can be applied for steady and unsteady state condition. Thus, this statement actually wrong. But for the development of Fick's law, we actually use here we consider this as a fixed law for steady state diffusion. For this deriving this equation, we assume that the diffusion is a steady state, and developing the second law, we assume that diffusion is a unsteady state. That is why this here we have one jx and here we have another jx plus delta x. This is because of unsteady state diffusion. If it is a steady state diffusion, here and here will be jx value. There is no change in the concentration. Okay, but this is a we derive the second law by assuming this is a unsteady state condition. But this is a misconception. Both the first law and the second law is applicable for steady state as well as unsteady state. Okay, the reason is this. This is the first law, J is equal to minus D into dou C by dou X. Second law, dou C by dou T is equal to D into dou square C by dou X. Okay, and here we can see the differential equation applicable at a point in time, at a point in space X. So actually we apply limit. During the derivation, we apply limit. Limit x tends to 0. Limit delta t tends to 0. Limited delta x tends to 0. So by applying the limit, actually this dou c by during the derivation, by applying this limit, this dou c by dou t changes to instantaneous time. Okay. In the derivation, we can see. Just a second. So in this derivation, you apply limit to delta t tends to 0 for dou c by dou t. So by applying this limit, actually this delta t changes to instantaneous time. And by applying delta x tends to 0, we change delta x into, or we change this quantity into instantaneous space position. Okay, so by applying this limiting term, this actually instantaneous space position, and dou t is the instantaneous time. So when the concentration changes with respect to time, then not valid, because here we use these two equations, or we develop these two equations by applying instantaneous time. So when the concentration vary with respect to time, is not applicable in this two equation. Okay, so here in this differential equation, we use instantaneous time and instantaneous position, and since we are using instantaneous time and position, the variation of this concentration with respect to time is not valid. So that is why we can apply these two equations or two laws for steady state and unsteady state. Okay, and one more thing is that for while deriving this equation, we apply this first law into the second law. Okay, so again, we use the first law to derive the second law. So again, we cannot use the steady state condition into unsteady state condition. Okay, so അതുകൊണ്ട് തന്നെ എന്താണ് ഇത് രണ്ടും steady and unsteady state use ചെയ്യാം. Okay, and one more thing is that in this case, if the dou c by dou t is equal to 0, for a steady state condition, dou c by dou t will be equal to 0. Okay, and then dou square c by dou x square, what is the value? That is also equal to 0. That means dou c by dou x will be constant. That means the concentration change with respect to position will be a constant value. Okay, so This is a means consumption. Fixed law and fixed second and first law can be applied for unsteady and a steady condition. Okay, that is about diffusion. And the application of diffusion, the diffusion play an important role when the materials are processed at high temperature. This is very important. And the rate of diffusion in normal temperature is very, very small. What is the reason? For all the diffusion which we discuss, the atom should have very high energy. Then only they displace from one position to another position. Okay. When the atom has higher energy, they can break the bonds. They can break the bonds and they can change the position from one point to another point. Okay. How this atom got enough energy? By increasing the temperature. When we apply heat into the material, the atoms got more amount of energy and they got an activation energy. They break the bond and they change the position from one point to another point. So the accelerating agent for the diffusion is temperature. So temperature play an important role in case of diffusion. We have to maintain higher temperature for proper diffusion. So commonly, if you want to change the microstructure or change the impurity, actually, or position of the atom, solute and solvent atom, we actually process the material at a very high temperature. So all the heat treatment process, we actually heat above recrystallization temperature. So in that temperature, the atoms got very high amount of energy and they diffuse from their positions. Okay. So melting and casting diffusion play an important role in solidification of metals and alloys. So during solidification process, the impurity atoms or alloy elements or solute atoms diffuse into the interstitial position or substitution position or lattice position. Okay. So in melting and casting, diffusion play an important role. And sintering, that is a diffusion play an important role in the material process using powder metallurgy. In powder metallurgy, the sintering is an important stage of powder metallurgy. We can produce materials by from a powder raw material. Okay, by sintering and forming, we can form different material from the powder. So that is the powder metallurgy process, where the sintering is an important stage, where diffusion play an important role. Surface hardening, we already discussed about carbonizing the surface of the gear in order to avoid the wearing of the gear or to improve the wear property of the gear. Okay, for that we provide a carbon rich surface for the gear. So where we use carburizing process. Similarly, we can introduce nitrogen into the surface by nitriding. So all these things are surface hardening process to improve the wear resistance property. For that, diffusion play an important role. Doping of semiconductor, we already discussed the doping process. We can introduce P and N type material into the original silicon or germanium atoms or doping process, where we use diffusion process. Oxidation of aluminum by the formation of protective layer of aluminum. There we can reduce different corrosions like problems in materials. And beverage bottle, PET bottles used for carbonate beverage, there also a diffusion play an important role. So these are the applications of diffusion process. So this is about your second module. Any doubt about this second law and fixed second law? Fixed second law. You have to study these two law, fixed first and second law. Okay, and there may be some problem based on this, and you have to search textbooks for problems. I'm only here. I'm only providing one problem, so you have to search textbooks for another problems, because in your syllabus the problem is included. See this simple problems. Okay. And here in case of X-ray diffraction also, simple problems may ask. So you have to study this. Any doubt about Fick's law? No. So this is your second module. We discussed different imperfections in the crystal. Surface defects, point defects, surface defects, and line defects, dislocations, prime red source, dislocation density, grain boundaries, and different specimen preparation process like polishing and etching, X-ray diffraction, and this is your assignment, SEM and TEM, then diffusion process. Okay, so this is the second module of metallurgy and material science. Any doubt?
Sir,
Yeah.
സാർ ഈ സെക്കൻഡ് ലോന്റെ ഒരു ഡെഫിനിഷൻ എന്താ പറയാ ഇപ്പം ചോദിച്ചാ സ്റ്റേറ്റ് ചെയ്യാൻ പറഞ്ഞ